Okay, so let us go a single linked list, second of review. Okay, so you all would know by now the motivation for using a linked list, first of all, is if you want to implement a list as an array, you need contiguous block of memory. So for example, like in this case here, you want to insert one more element and the array is full, you have to double the size of the array. So you have to create a new array which is double the size of the previous array. So that means you need contiguous block of memory available to store that many elements. Now, it may not be possible always to find such contiguous block of memory for an array, especially if your list size is larger. Again, list is an ADT. You could implement a list as a dynamic array or using a single linked list or a double linked list. So that's the motivation to go for a linked list. So in a single linked list, you will have what is called a node object that stores the data. So if this is the list that you want to store, say 20, I hope everyone can see my PowerPoint, right? Is there anyone who cannot see my PowerPoint?
I can see.
Okay.
I can see it too.
Okay. So if this is the list of data, integers that you want to store, in an array, you will just store them in consecutive block of memory like this. But if you want to store using a single linked list, you need to package it as a node, and each node will have a member variable called data in for which you can set to this value. But in addition to the data, each node should also store the address of the next data node. That is how you can traverse the contents of the linked list. Okay, so you need what is called a node class that will have two member variables. One is the data that you want to store. It could be an integer, it could be a character, it could be anything. It could be even an object. Okay, it's like if you want to store an employee object, you could do that. Then the next node pointer is the name of the pointer that stores the address of the next data node. So we'll call the node class. So node star means it's a pointer. So next node pointer is a pointer that stores the address of a node. That's what this means. You all know what is a pointer. So now, in addition to the data nodes, you need to also have to have a dummy node called the head node that is kind of the first node of the linked list. And so the head node has the address of the first data node. So this node is our first data node at address 120, and the head node also is a node, is of type node, so it has a data field as well as the next node pointer field. We don't set up anything for the data, but we set the next node pointer for the head node to be the address of this data node. So based on this, if you look at the list class, so we have two classes, you should remember. So the node class, each individual unit of a linked list, and then the list class that basically represent the list, the linked list. Okay. Now the member variable there is just one thing called the head pointer, and it's a pointer for the of type node. So that means it stores an address of some node, and what node it is, it stores the address of the head node. So this is how you initialize or create that list. The in the constructor for the list class. So you say new node, you're creating a node, and when you say new, you're basically allocating dynamically space in memory, and the address of that space will be stored in this head pointer. So the head pointer stores the address of the head node. So for example, this is something like this. The head node is, this new node is created at address 100. The head pointer stores that address 100. So using the head pointer, you can access the head node. So as part of initialization in the constructor, we can right away go ahead and set the next node pointer value for the head node to be null. This is because you're just creating the list or setting up the list. You're not yet populating it with data. So the list is empty. So this is how you would set up the list. So set the next node pointer to null, so that there's no, it indicates there's no data node and the list is empty. Now, how would we, I'm just thinking how to proceed with this covering. All right, so now, so if you want to access, say, the linked list, what you do is start with the head node by using the head pointer. So let us look up this list. So the head pointer stores 104, that's the address of the head node. So using the head pointer, you can access the head node, and in that head node you have the next node pointer field that stores the address of this first data node. So from here, from the head node, you can visit this data node and access the data. And then from that node, you can visit the next data node, which is at address 136, which is this one. And there you have the data. And then access the next data node, which is at address 156. And the next data node is at address 176. Then the next node pointer for this data node is null. So that means this is the last data node. You cannot go anything further down. So that is how we access a linked list in the forward direction. And you can access only in one direction, from the head node all the way further down. Now, we saw this insert code. So let us look at the insert at index. That will be more general. So if you want to insert to a linked list at any specific index, so this is a member function, insert at index, and we pass the data that you want to insert and the insert index where you want to insert. So this procedure is going to be useful to access any linked list and insert or delete or anything. So let us look at this code. So as I said, you can traverse the linked list starting from the head node. So you need a handle to the head node. So the head pointer has the address of the head node. So use the head pointer. This is a member variable in the list class, and this is a member function in the list class, so you can access the head pointer. So call the get next node pointer function on the head node, basically. So head pointer arrow means you're accessing the head node, and call the get next node pointer function on the head node, and that will return the value of this next node pointer value in this head node, which is 200. That's the address of, yes.
What you say?
What? Any question?
And you think you slick something, so you think another car just came. No, I think
I am not able to see.
You see that? She definitely heard that. Can you get up? No, my stomach has anything she let me.
What is that sound going on?
Please. Look at you. My leg and my stomach hurt.
Okay, somebody's microphone is on.
And you don't be letting me sit on you half the time. Just go sit outside. It ain't that hard. I gotta take orders anyway.
Okay. Whose microphone is on? All right. Okay, so this statement gives you access to the first data node. The head node, access using the head pointer, arrow, get next node pointer returns the address of the node next to the head node, which is this node. And we'll call that as the current node, and the pointer that stores the address of that node as the current node pointer. So using the current node pointer will be this 200, storing the address of this first data node. Now we'll set up a local variable called index equals 0 to keep track of the index of the nodes we are visiting. So right now we are visiting the first data node. So if you consider this as an array, it would be say considered as index 0. So that's why we call it as index equals 0, representing the first data node. Now we have to traverse to the list and reach a specific index, which is insert index equals say 2, and then stop there and insert our data 30. That's what we're going to do now. So using the current node pointer, go through one node at a time, and this is the condition. You can go through the nodes only if the current node pointer is not null. If it is null, it means you already reached the end of the list. So current node pointer is 200, it's not null, so you can get inside the loop and check if you have reached the index where you want to insert. So index equals 0 currently, insert index is 2, so 0 not equal to 2, so you don't break from the loop, continue the rest of the loop. So we will set now our previous node pointer, which was initialized to the head pointer, pointing to the head node. So now the previous node pointer will be assigned the value of current node pointer. So basically you're moving these two pointers to the next node. So you first move the previous node pointer to point to the next node, which is the data node here. So when you say previous node pointer equals current node pointer, the previous node pointer takes the value 200. And then you move the current node pointer to the next data node. So current node pointer, arrow get next node pointer, will return you the address of the node next to the current node. So that's stored in the next node pointer member variable in the node class. So the 70 will be now the value of current node pointer, and you also increment index from 0 to 1, and then continue the process. So current node pointer is 70 not equal to 0, that's true. So come inside, index is 1, insert index is 2, they are not the same, so continue further down. That means you have not yet reached the index where you want to insert. So move the previous node pointer to the next data node, which is this node at address 70. So previous node pointer becomes 70, and current node pointer is moved to the next node. So using current node pointer arrow get next node pointer, you can get the address of the node next to the current node, which is this 500, and that will be the new value for current node pointer, 500, and index is incremented so from 1 to 2. So now when you go through the while loop, index equals insert index, so you break from the loop, and you reach now the code after the while loop where you're really inserting the new node. So you create the new node, and let us say it is created at address 900. So that's now the value of this new node pointer that stores the address of this new node, and then you can set the data of the new node to 30. Now this node is not yet linked to the list, so in order to link it to the list we have to use these two statements. Now currently the list is like this, so we have to break this link and kind of insert this new node. So how to break that link and insert? So let us do this now. We'll link the new node to the node that is supposed to be following it. So we are currently at this insert index 2, and we want to insert this new node there so that this node becomes the node following that newly inserted node. So the new node pointer stores the address of this node, so using that you can access this new node. Arrow set next node pointer to be current node pointer. So current node pointer is 500, pointing to the referring to the node at index 2. So now we can make that to be the node at index 3 and insert this new node. So now from this new node we can visit the current node. Now still we have not yet broken the link. So this link is from this previous node to this current node. So if we change this address of this previous node to this new node address, which is 900, we will be setting up the link from the previous node to the new node. So we do that by doing previous node pointer arrow set next node pointer equals the pass the value of new node pointer, which is this 900. So that way you can create this link. So now you can traverse the link from the head node, starting from the head node all the way to this previous node, and from here to this new node, from here to the current node, and then so on. Okay, so any question on inserting at a specific index? Okay. Now for the delete, let us go through the version I gave you guys for the question 1. So you can work on that. Okay, so we want to delete okay, so question 1 is to delete all occurrences of a data in a linked list of a specific data. So for example, if your list is something like this, so it has, I'm just typing the data values. So something like this. You want to say delete all occurrences of 45 in this list, so that, so from the main function you create the list, integer list, fill it populate with elements, and then ask the user to enter a data to delete, and let us say user enters 45, and you call the delete all elements function on this integer list. So delete all elements is going to be a member function of the list class, and you pass that 45. So when you come out of this function, all the occurrences of 45 should have been deleted from the list. So if you try to print the list after you call the delete elements function, only the rest of the elements without any 45 should be printed. So it should be like 20 followed by 23 followed by 32 followed by 34. This is how the list should be after you come out of this function. So that's what we want to accomplish. So the code that I gave you all as part of this assignment or question will delete an element at a specific index. Okay, and we can use this logic to come up with the code for this. If you want, you can add a member function called delete element at with data. Now that function will delete only, so delete let us say delete data. So that function could be very similar to the delete element function, but it will return only the first occurrence of a data. Okay, so let us go through this function, delete element function, and when it comes the time to modify this function, delete element at a specific index to delete a specific data, I'll tell you what changes to make, and then you can build on top of it. Okay, so let us look at the code for delete at a specific index. Okay, so I'll use this example. So let us say the list is currently 10, 5, 37, 9, and delete index is 2. So you want to delete the element at index 2, which is this 30. So after you delete it, the list should be 10, 5, 7, 9. So for that, again, we will make use of the current node pointer, previous node pointer, and also another pointer called the next node pointer. And we'll see the purpose as we go through this code. So first, let us set up the current node pointer to point to the address of the first data node. So that will be done using, as usual, head pointer arrow get next node pointer. So we are getting the address of the node next to the head node, and that is stored in current node pointer. And previous node pointer takes up the value of head pointer. Next node pointer also takes up the value of head pointer. So things will be like this. Current node pointer stores this address 200, that's the address of the first data node, and index will be set to 0. And previous node pointer is taking the value of head pointer, so it's really pointing to the head node, and the next node pointer is also pointing to the head node. So that's how the pointers are set up. Now go through a loop. Current node pointer is not null, so get inside and check if you have reached the node at a specific index that you want to delete. So index is 0, delete index is 2. Now if you want to modify this code for deleting a specific data, instead of checking the index, you could check like what? You could check if, let me do it here. So we can check if you have reached the node that has the specific data that you want to delete. So you can check if current node pointer arrow get data equals the data. So that means you have reached the node that you want to delete. So that's the only change you have to make to this delete element at a specific index to deleting a specific data. So when we have reached such a node, so let us assume that we have reached this 30 that we want to delete. So we can set the next node pointer to take up the value of the node next to that current node. So the current node is really pointing to this 30, node with data 30, and we can make this next node pointer to take up the value of the next node pointer of the current node, which is this 500. So we do that. We can say current node pointer arrow get next node pointer will return this value, this 500, and assign that to the next node pointer, which was initially pointing to the head node. So the next node pointer will now point to the node next to the current node, and that's the address that you're storing, the 500, where that node is. And then you break from the loop. So after you break from the loop, basically you see the link was now between this previous node to the current node, and from this current node to this next node, and so on. So you want to break this link. So this is a single linked list. So if you break this link, this node will get isolated, the current node will get isolated, and that's what you want to kind of simulate, in the sense that we should not be able to visit this node with data 30. So how we do that? So using the previous node pointer, which will be pointing by that time the node previous to the current node, so that's this node at address 70. Arrow set next node pointer. So set the next node pointer for the previous node to be this next node pointer value, which is 500. So previous node pointer arrow set next node pointer is now set to 500. It was previously pointing to this node at address 900. So that was the link that was there. So breaking this link and making this previous node's next node pointer to take up the value 500. So with that, you have kind of logically isolated this node, and we can go from the head node to this previous node, and from here to this next node, and so on. So that's the only change you have to make to this code to implement this delete data function. So of course this one will delete only one occurrence of, say, let us say if the data is 45, it will delete the first occurrence of 45, and the list will be like 20 followed by 23, and then followed by 45, followed by 32, and followed by 45, and followed by 34. So I think I almost gave you how to do it. So now we have to think about how we can implement the delete all elements function that will make use of this delete data function and repeatedly delete the data. So think about how to do that. Okay. So let me save this. So I'll post this code in Canvas after this review session, so everyone can access this code. Any question? So I think I pretty much covered the linked list, single linked list with this. So if you have any questions, you can ask.
Okay. I understand question 2, but for when we're running the program, do we have to run it together, like both the array and the list?
No. So there, as I said, there are two separate programs.
Okay.
For some reason I cannot see it. Yeah, so how do I see who are all there? One second. Oh, if I stop sharing, it comes like this. Okay. All right. Yes. So I gave you two separate code. One that works with an array. So the list is implemented as an array, and then you will implement the selection sort function that will sort the list. So the main function, you get the maximum value as input from the user, and the list size is something you are varying from 1000 to 20,000 in the increment of 1000. So all this code has been already set up for you in the main function. You don't have to change anything here. So the list is populated with data, and you're calling a selection sort function and passing the integer list as argument. And so this is the function you have to implement with the selection sort algorithm. And we saw in class a pseudocode of selection sort. Let me go over that little quickly. Okay, so this is selection sort. So the idea is you go through a sequence of iterations, and in each iteration what you will do is, so the iteration index is actually used as a loop, as the index, as a loop index basically. So in iteration 0, corresponding to index 0, you are trying to find what is the element that is the minimum element starting from index 0 and bring that element to index 0. So that's what we are trying to do. So at index 0, iteration 0, we are trying to bring the minimum element starting from index 0 to that index. So in order to do that, we will do this process inside the loop. So we'll set a temporary variable called min index to be that index, iteration index I itself. So it means we're assuming initially the index of the minimum element starting from index 0 is index 0 itself. So that's why min index is set to I, index 0. Then go through a loop inside, starting from index j equals I plus 1 to n minus 1. So starting from the next index to I, which is I plus 1, go all the way to the end of the array, n minus 1. And check if a of j, so that means have you come across some index at j where the data there is less than the data that you currently think is at the min index. If that's the case, you can set your min index to be that index where the lower data, value data is. So if you go through this process until the end of the array, by the time you come out of this inner loop, you would have found the index where the minimum data is, starting from index I, which is 0. And then you swap the data at index I with the data that you have found to be at with the minimum data at min index. So if you do that here, j will be starting from 1, we go all the way to 9. So currently the min index is 0 and the data there is 5, and you're comparing a of j, which is 6, with 5. So 6 is greater than 5, it's not less than 5. So we just keep moving. Now we encounter 5. 5 is again not less than 5. 5 is equal to 5. So you want to check if some data at index j is less than the data currently at min index. Now we have j to be 3 and that a of j is 4. Now 4 is less than 5. So min index, which was set up to 0, the iteration index, is now set to 3. So min index will be 3. That means the data we have found as minimum by now is 4. So let me write that here. So min index would be now 3. So now j will be 4 and the corresponding data there is 3. So checking if a of j is less than a of min index. So a of j will be 3, less than a of min index will be 4. Yes, 3 is less than 4. So your new min index will be the j value. So that is now set to 4. And you now compare the rest. So 10 compared with the data at min index, which is 3. So 10 is not less than 3. Then 9 is not less than 3. But say 1 is less than 3. So our new min index will be that j where 1 is. So that is this 7. Then compare 7 with 1. 7 is not less than 1. 8 is not less than 1. So that's the end of the inner for loop up to j equals n minus 1. So you come out of that for loop, and by the time you come out of the for loop, as I said, you would have found the index where the minimum data is, starting from index I equal to 0. So that's the first iteration. So I equals 0. Still we have not changed I. That's the iteration index also, so it stays the same for that particular iteration. So what we'll be doing is we'll be swapping the data at index I equals 0 with the data at min index, which is 7. So you're swapping 5 with 1. So 1 comes here, 5 goes to this index. And this is what you do repeatedly. So in the next iteration, your I will be 1. And you're assuming initially min index is also 1 to begin with. So min index is also 1. So the corresponding data is 6. So you will run the j loop from I plus 1, which is 2 to n minus 1. So at I plus 1, so at j currently we have 5. Compare 5 with 6. Is 5 less than 6? Yes. So we can update our min index to be that corresponding index j, which is 2. And then keep moving. Then 4 compared with the data at min index, which is 5. 4 is less than 5. So that means we have to update that min index to 3. Then 3 compared with the data at min index, which is 4. 3 is less than 4. So that's the new min index. Now 10 compared with 3. 10 is not less than 3. 9 not less than 3. 5 not less than 3. 7 not less than 3. So by the time you come to the end of the array, you would have found index where the minimum is, starting from index I equals 1. So that min index is 4 and the corresponding data is 3. So we'll be swapping the data at min index, which is 3, with the data at index I equals 1, which is 6. So 3 comes to index I equals 1 and 6 goes here. So you see, but in each iteration you're moving one element to its final position. So in iteration 0, you're moving the element that is supposed to be at index 0 in the final sorted array to that position. And then in iteration 1, which is corresponding to the second smallest element at the end in the sorted array to that position. And the third iteration will be moving the third smallest element to its position. So you keep doing that for n minus 1 iterations, because after that n minus 1 iteration, the last element could be considered to be in its position. So by the time the maximum element would have been moved to its final position. So that's why you run this I loop from index 0 to n minus 2, that corresponds to the n minus 1 iteration. Okay, so this is selection sort, and so this is almost given for an array. So of course we are implementing the list as an array. So how would you access, say, you cannot say a of I here, right? So list is the object name, so list dot read at a specific index. So using that you can read. So there's a read function here, So you can read. So if you want to access the element at a specific index as part of a selection sort algorithm, you can read that element. Now if you want to modify, you can modify. There's a modify element function, and you pass the index and the data that you want to modify it with. So that will modify the data. So this is how you can access the contents of the array using the member functions of the list class. Now the same thing could be done for a single linked list. So in the single linked list, you have again the member functions to read at a specific index, then member functions to modify the element at a specific index, and so on. So you can use a similar logic to do that. Now in the case of single linked list, the thing you have to do here is with an array based implementation, what we found is starting from a specific index, right? We want to find where the what is the data, what's the minimum data and where it is. So that's what we found here. So starting from I equals 0, what is the index where the minimum data is, and that happened to be at index 7, and that's the minimum data. So then once you found the index where the minimum data is, you swap the data at that index with the data at index I equals 0. Now in the context of a linked list, that would be like what? You have the current node pointer pointing to the node, a specific node. So that's our current node. And we want to find which node, starting from the current node, has the minimum data. So, and when I say which node, we want to find the address of that node that has the minimum data. In the context of an array, that would be min index is 7, right? So similarly, for the linked list case, we have to find the address of the node that has the minimum data. And I already gave you the function that finds that for you. So starting from a particular node, so the current node pointer is pointing to a particular node. Starting from that node on this list, what is the node that has the minimum data, and what is its address? So this function does that for you. So it's the logic is similar to how we did for the array here. So like min index is our min data node pointer. So we set our min data node pointer initially to be the current node pointer, like we set the min index to be the iteration index I, right? So initially set min index to be I. We are setting here the min data node pointer to be the current node pointer, and then go through a loop like the J loop. Now before we get into the loop, move the current node pointer to the next node and check if it's null. So this is in a single linked list, so you have to move through using the current node pointer. So move the current node pointer to the next data node and see if that node is existing there. So if current node pointer is not null, that node is there. And just compare the data of the node pointed by the min data node pointer, that's like our min index, the data at min index compared to the data at index, that the node that we are, that is our equivalent to index j, where the current node is, the current node pointer is. So if the current node's data is less than the data that is currently pointed by the min data node pointer, then you can set the min data node pointer to current node pointer. So this is like if the data at index j is less than the data at min index, we can set min index to be j. So if you want to, you can write down min index is equivalent to the min data node pointer. So I just say equivalent to min data node pointer, and current node pointer is equivalent to the j, index j. So this will help you to kind of compare this code with the pseudocode for selection sort. So you keep going through the while loop, and you as you see the j loop will go up to n minus 1. So the current node pointer goes all the way to the end of the loop, end of the list, and then when you come out of the loop, you have the min index, that's the appropriate value. That has the minimum data starting from the current node. So you return this min data node pointer to your selection sort function. So and then when you come back to the main code, the selection sort, here you will swap the, again you use, so you basically get the idea here. You write this outer for loop using the current node pointer in the selection sort code, and then call the find minimum data node address function within that within that loop, and then that function will return the address of the node with the minimum data. Okay, let me show it here like this. So this is inside, say, the selection sort code. You will try to find the address of the node with the minimum data starting from the current node pointer, and then, like I show here, you swap the data of current node with the data that has a minimum with the node that has a minimum data, and then run the next iteration by moving the current node pointer to the next data node. So I hope that is clear. So we will run, I'll just write it like this. So run a loop using current node pointer inside the selection sort code, and then call for each iteration of this loop, for each iteration of this loop, call the find minimum data node address function to find the address of the node with the minimum data starting from the current node. So once that function returns the address of the node with the minimum data starting from the current node, so let me index this so it can look like a loop. So now you come out of the loop and swap the data at current node with the data that has with the node that has the minimum data found using the find minimum data node function. So you're calling this function to find the address of the node with the minimum data starting from the current node. And once you found such a node, you swap the data of the current node with that node, and repeat this process, then move the current node pointer to the next data node and so on. That will get the list sorted. Okay, and you can use the same logic for an array too. An array is going to be very similar to this pseudo code. So it is for the list, you have to think a little bit, but as I showed here, the mapping, you run, you run a for loop using or while loop using the current node pointer and the selection sort algorithm, and inside the minimum data node address function we have another current node pointer, but this current node pointer scope is within this function. So it starts from the current node and goes and finds the node with the minimum data and returns that address. So this current node pointer is different from that. This is within this function, the selection sort function. If you want to avoid confusion, you can name this current node pointer anything else. Okay. Is that clear? Any question?
Yes, it did. Thank you.
Okay. Alright, I think this should have answered second person question on question 2. You wanted to go through dynamic array, and we kind of went through that and selection sort code and stuff, right? Is there any question?
Sir.
Okay, good. Alright, so any question, anything else? This is coming on the top, so okay. So the third question we went through pretty much it in class. So it has to also do with sorting, but it's not selection sort or anything. So in the third question, you have to create a list with each insertion, and as you insert the elements to the list should stay sorted like this. So you start initially with an empty list, And then when you insert 10, of course that's the first element, so you can insert it and the list will stay sorted. Now you want to insert 3, so to this list that has 10 in it. So you have to determine what's the appropriate position where you can insert this 3 so that the list will stay sorted. So you have to insert the 3 before the 10 so that the list will be 310. Now the next element you want to insert is 5 to this list 310. So you have to find the appropriate location where you should insert this 5 so that after the insertion the updated list, which will be 3 5 10, should be sorted. So let us do one more case. So you want to insert now say 12, so where should we insert 12 to this list so that the updated list gets sorted, and it has to be inserted at the end of the list because 12 is greater than every element. Now for 7 you have to insert between 5 and 10 so that it will be 3 5 7 10 12. So the idea is for each insertion you have to traverse the list starting from the head node and find the appropriate index at which you have to insert. Same thing with an array also. Starting from index 0, you have to traverse through the array and find the appropriate index where you can insert so that the array will stay sorted. So that means let us do this for 7, the logic. So you will compare that insert data, which is 7, with the node, the data of the nodes that you are visiting. So let us say current node. Okay, so current node's data is 3 and 7 is greater than 3. So that means 7 should not be inserted before 3. You're trying to insert where you're trying to see where you can insert. So can we insert 7 before 3? No, 7 is greater than 3. So move the current node pointer to the next data node. So current node's data is 5. So is 7 greater than is 5 greater than 7? No. So we have not yet reached the index. Now is 10 greater than 7? Yes. So 3 is not greater than 7. So 7 should not be inserted before 3. 5 is not greater than 7. So 7 should not be inserted before 5. But 10 is greater than 7. So that's the position where you want to insert. That's the index. The index of 10 should be our insert index. So you all in that function, that code I gave you for the third question, the other functions like insert, at index, everything are already there. So once you have found the index where you have to insert, you can call that function insert at index and insert that data at 7 there. Okay. Similarly, in the case of an array, you have the insert at index function that you can call by passing the index where you have found to be the appropriate index to insert the data. So that will take care of inserting that 7 to that list and you get the updated list. Okay. So you don't have to really write the code by yourself to insert at that specific index. Once you have found the appropriate index using your code, you can call the other function insert at index and insert the data. And in class we went through a similar example where I said you want to insert at an appropriate location. So and that the inversion, no, this one. So inserting at an appropriate location decided at runtime. So what this code does is, okay, the application here is this. You want to maintain a list of integers such that the list always has all negative integers followed by all positive integers, and the user is inputting the integers. So for each insertion you have to maintain that list should be always containing first all negative integers and then followed by all positive integers. So like here, the user enters initially 23, that's the first element, so it could be inserted right away. Now 10 is kind of positive, so now positive you don't have to sort things, you can insert at the end of all the positive integers. Now negative 45. So you have to traverse the list and you have to check if the current node's data, which is 23, is what you call positive, because you want to now insert a negative data. So that means you have to insert the negative integer before the first positive integer. So if you want to now insert negative 78, you traverse the list, it is negative 45, so it's still negative. The next node data is 23, which is positive. So you have to insert the negative 78 there. So for negative elements, if there are already negative elements, you want to insert at the end of the last negative element. So if you want to insert, say now negative 11, you want to insert negative 11 after the last negative element. So logic similar to what we just went through. You scan through the list. Now in this example, the moment you come across a node with the positive data, that's the index where you want to insert. So in your assignment for this question, the corresponding scenario is you scan through the list. The moment you come across a node whose data is greater than the data that you want to insert, that's the index where you have to insert the data. So that's the similarity between this code and the code in the slide for finding the index to insert dynamically. So that's the code here. So you scan through, and when the current node's data is positive, greater than or equal to 0, you break the loop and insert the new node. And in this case, you have to compare the current node's data with the data that you want to insert, and you can call it as insert data if you want to, and compare that with the current node's data, break from the loop and insert the new node. So it's going to be quite easy if you understand how to do this function. Right, so I'm trying to give you as much code, help and things, logic, everything to do things easily. So I hope you make use of these things. Is that clear? Any question?
No question.
Okay. Let me see if I had to stop, pause, share. I think that will, no. Okay, so in order to chat, I have to stop sharing my screen. Okay, I can still chat. Okay, so it's still recording. So if there are no more questions, we probably can stop with this. Okay, what time is it? Okay, it's almost time, 7. So we'll have another review session on Monday. So if you want, the people who attended this session or anyone, because I'm going to record this video, it's already recorded, so I'm going to post it in YouTube, as well as Zoom is going to generate a recorded video. I'm going to post that too. So anyone in class who can go ahead and work on this weekend and implement all these things, and if you have any questions, you can come back on Monday and ask any specific questions you have. And people who could not attend today's session could also join on Monday and ask any questions you have. Okay, so make use of this and work on this weekend and implement the code, and if you have any questions, you can come back on Monday and ask me, right? So we'll have another review session on Monday at 6 using again this Zoom. Right, so let me stop sharing, and if there are no more questions, we will finish for today, and we will meet again on Monday. Right? Okay, have a nice weekend and work on the code.